1.1 or Module 1, Lesson 1 is on precision, accuracy, and significant digits. So here, the intro, what we need to be able to get through this lesson is to know how to round. The rules on rounding are, if the number you are rounding to has a 5, 6, 7, 8, or 9 after it, then you're going to round that number up, meaning you're going to add 1 to it. If you are rounding a number that is followed by 0, 1, 2, 3, or 4, so anything less than 5, then you're going to round down, meaning you're going to leave the number as it is. And all the numbers after it, or to the right of the number you just rounded, are going to turn into zeros. Okay, so for example, we have the number 382,578, and we're rounding to the nearest thousand. So this is the ones place, this is the tens, hundreds place, this is the thousands, right? This is the one we're paying attention to. Now to the right of it, there's a 5. Since that means we're going to round up, this 2 is going to turn into a 3. So everything to the left stays the same, the 38. Then this 2 turns into a 3. And to keep the place value, those numbers to the right are going to stay as zeros. They're not going to go away. They're just going to become zeros. So this is the number we'd round that one to. Then if we're rounding 5,809 to the nearest 100, so here this is the ones place, the 10, the hundreds. So that 8 is what we're going to round either up or down. The number to the right of it is a 0. That means we're going to round down. Everything to the left stays the same. That 5 doesn't change. The 8 stays the same because we're rounding down. And the numbers to the right become zeros. Now we have 5,800. Next one. So 0.33941. I did not give myself any space there. We're going to round this to the nearest thousand. So thousandth, meaning 3 places from the decimal, right? This is the tens place, the tenths, the hundredths, and the thousandths. I'm not good at saying the TH part. Okay, so that 9, everything to the left stays the same. 0.33 stays the same. This 9 is either gonna go up and increase this one, or this, depending on this number to the right. That 4 means that we are going to round down. So that is going to be a 9 still. That is our final answer for that one. Last one, 45.321. Round to nearest hundredth. So again, this is the tenths, this is the hundredths. Everything to the left is going to stay the same. So 45.3. This 2 is going to round down because of the 1, right? Less than 5, you round down. Stays a 2. And we don't need the 1 to become a 0 here because it's not holding any place value. Okay, so that is lesson on rounding. Vocab for the precision, accuracy, and tolerance part. Definition of precision. Precision is how close measured values are to each other. So if you throw multiple darts and they all end up around the same place, you have high precision. If they're all spread out from each other, it's low precision. Accuracy is how close you are to, how close the measured value is to the actual value. So where you want the value to be is, say, in the center of that target. If your arrow hits that center of the target, you're said to have high accuracy. If it's far away from where we want it to be, like far away from that middle point, then we say it's low accuracy. Significant digits. Digits that have significance or meaning and give more precise details about the value of a number. They measure overall relative accuracy of a value. So we're going to talk through what all those numbers mean. And then tolerance This is an allowable variation of a specified quantity that is still considered acceptable. So here we have 125. It's allowed to be 5 units greater, 5 units less than that main number. So it can go up to 130 and down to 120. Accuracy and precision. So in everyday speech, we tend to use these like as if they mean the same thing, but in scientific meanings, they're very different. Accuracy is a measure of how close the measurement is to the corrected or accepted value. And precision is how close a series of measurements are to each other. So darts thrown at a dartboard can be helpful for illustrating this idea. So here on the low end of precision, we see these examples are the darts are very far away from each other. And then on the high end of precision, they're very close to one another. How this relates to accuracy. So accuracy down here, low accuracy, they are very far from the center point of the target, like where we want them to be. And then high end of accuracy, they're very close to the middle of that target where we do want them to be. So when you have low precision and high accuracy, they're close to the middle, but far away from each other. High precision, high accuracy, they're close to each other and in the middle. So that just explains. So here, significant figures, they're a measurement that consists of certain digits in the measurement plus one uncertain or estimated digit. In this illustration, we have the bottom ruler that measures a length with 2 significant digits, the 2 and the 5, while the top ruler, it has 3 significant digits, the 2, 5, and another 5. In a correctly reported measurement, the final digit is significant but not certain. So your last digit is significant, but it's always the uncertain digit. So down here, this 5/10 is uncertain, and up here, the 5/100 is uncertain. It talks about if you had a different ruler, there's not really a ruler that measures in the thousands place. So this would always be so uncertain, you wouldn't need to include it. All non-zero digits in a measurement are significant. This is the first significant figures rule. All non-zeros, meaning all numbers that are not 0, are significant, meaning 1, 2, 3, 4, 5, 6, 7, 8, 9 are all significant, always. So 237 has 3 significant figures because the 2, the 3, and the 7 are all significant. 1.897 doesn't matter that some of those are like decimal places. It's still 4 significant figures because they're all not zeros. So how many significant figures are there in 734.898? This is not 0, so it counts. We have 1, not 0, not 0, not 0, not 0, not 0. Just count the number of numbers. That's 1, 2, 3, 4, 5, 6. So this is 6 significant figures. We just say sig figs. Second rule, zeros between non-zero digits are always significant. So 39,004. This is significant, this is significant, this is significant because they're not zeros. These zeros are between 2 non-zeros, so they do matter. So 3 here, 4, 5. This is 5 significant figures. So zeros between non-zeros. Also the 5.02, the 0 is between the 5 and the 2. That one counts. So there are 3 there. How many significant figures are in 83,740,034? Say 1, 2, 3, 4, 5, 6 because they're not zeros. 7, 8 because they're between 2 non-zeros. This is 8 significant figures. Zeros in front of non-zero digits are called left end zeros. They are never significant. So all these zeros leading up to the 8 are not significant. Only the non-zero or the 8 matters. So we say there's only one significant figure. Here also, all the zeros leading up to the non-zeros do not matter. So 4, 1, 6, those are 3 significant figures. In this example, those zeros leading up to the 5 and 2 are not significant because they're on the left end. 5 and 2 are significant. That's 2 significant figures. And right end zeros here, so zeros that appear after non-zero numbers are right end zeros. Those do not matter, so they're not significant. So 140, the 1 and the 4 are non-zero, so that's 2 significant figures. That 0 at the end is not significant, so we just have 2 significant figures. 75,210, that 0 on the end is not significant, so we have the number of numbers 1, 2, 3, 4 significant figures here. How many significant figures are in the number 90? So if we say that right end 0 is not significant, we just have the 9. This is one significant figure. And right end zeros in a number with a decimal are significant. So 620.0. This has the 2 non-zero numbers are significant. This decimal after this, this is going to make this 0 before the decimal count and this decimal after. So this we say has 4 significant figures. 19.000 has 5 significant figures because of this decimal, right? The 2 non-zeros and then the 3 zeros after the decimal. So how many significant figures would there be in 89,700.00? 8, 9, and 7, that's 3 significant figures. This decimal makes these zeros matter. So 3, 4, 5, the zeros after also count. So there's 5, 6, 7. 7 significant figures. Last rule about counting numbers and conversion factors. So in lesson 3, we're going to talk a lot about conversion factors. They're just relating one measurement to another, like 1,000 millimeters equals 1 meter. This has unlimited significant figures and infinite precision because they are exact relations, and 25 people, like any counting numbers where you count the exact amount of something and don't take a measurement, these have unlimited significant figures and infinite precision because they are exact, right? There's not like 2.5 people that you just counted 2 exactly. So when we have something like 75 dogs, counted 75 dogs, that is going to be unlimited significant figures, right? It could be 0.0000, all those zeros matter because we know that it's an exact count. So infinite precision and unlimited significant figures. Rounding using significant figures. So once you've determined the number of significant digits in a measurement, you want to round to a specific number of them and keep the place value. You count the number of significant digits and then apply the appropriate rounding rule. You're counting from the left to the right. So here we say round 143,753 to 4 significant figures. So counting from the left, 143,000. So 1, 2, 3, 4. That's the 4th significant figure, the 7. These are all non-zero numbers. They're all significant. So this one is either going to round up to an 8 or stay a 7. The right number is 5. That means we round this up. 143,800. We want to turn these into zeros to hold the place value. So that would be the final answer to that one. Example 2, rounding 0.007656. Leading zeros are not significant. So when we're counting 3 significant figures, starting at the 7, that's 1, 2, 3. This is my 3rd significant figure. It's going to round down because of the 4. So we have 0.0076. And this is my last significant figure, stays a 5. There are 3 significant figures here, just like we wanted. Okay, here we're going to go into more with accuracy and precision. So a measurement that is more precise means that it has more decimal places. And a measurement that is more accurate, we're going to see how many significant figures. It should have more significant figures. Suppose you are using 2 different tools to measure the thickness of your cell phone. You measure with one tool that says it's 0.31 inches, while the other is 0.312. So which one is more precise? The one with more decimal places. So this one goes to the thousandths place. The second one goes to the thousandths place. The first one only goes to the hundredths place. So 0.312 is a more precise measurement. And the one that is more accurate is the one with more significant figures. The leading zero does not matter or is not significant. So the first measurement has 2 significant figures and the second one has 3. So 0.312 is also the more accurate measurement. It's more accurate and more precise. Example 4, a car part is used to measure 2.5 centimeters. It is coated with a film that is 0.025 centimeters thick. So which measurement is more precise? This one only goes to the tenths place. This one goes to the thousandths place, right? 3 from the decimal. So this one is more precise because more decimal places. And here, 0.0, these are not significant. The 2 and the 5 are, so this has 2 sig figs. The one up here has these 2 non-zero numbers are significant, so they both have 2 significant figures. Neither more accurate, neither is more accurate, same number of significant figures. Number 5, a section of newly complete road is 9,320 feet long, and the concrete surface is 0.8 feet thick. Looking at these, which one is more precise? This is the only one with a decimal place, so this one is more precise. Which one has more significant figures? 1, 2, 3 in the first one, right? This 0 at the end is not significant, so right end 0. So 3 significant figures here. This one has 1 significant figure. This is a leading 0. So here the 8 is the only significant figure. So we'd say this one is more accurate. Okay, tolerance, the last part of this lesson. Another way to determine the accuracy of a result is to measure, is a method known as tolerance. Tolerance allows us to measure an interval that gives us an allowable margin of error. So how much you can differ from the exact point that they want you to get. It's actually like if I say you're going to get an A if you get a 95% in this class, plus or minus 5, right? So that's the degree of error you can get above a 95 by 5 points, or by 5%, and still get an A, and you can go down 5% all the way to 90 and still get an A in the class. That's the allowable measurement, or the allowable difference from that center point. when given tolerance, we can find the minimum and maximum possible values. So if you subtract that allowable difference from the original number, it's going to give you the minimum value. And if you add it, then you're going to get the maximum. A factory produces pencils that are 19 centimeters long with a tolerance of plus or minus 0.05. So if I add 0.05, that's going to give me my maximum. That's going to be 19.05. That is my maximum allowable value. My minimum is going to be when I subtract this. So my minimum comes from subtracting the 0.05 from the 19, get 18.95. That's my minimum value. The range is going to be from my minimum allowable value all the way to my maximum. And this number right here should be at the center point between these two. So that is my range.